Good afternoon, everyone, and thank you for attending our Specifying PCB Laminates to Your Performance Needs webinar. My name is Keith Rujo, Marketing Manager here at Epic. Before we get started, just wanted to let you know you'll all be muted during this presentation. If you have any questions as we move along, please enter them into the questions panel located into the webinar control panel, and we'll try to get back to them, get to all of them at the end of the presentation. If we don't have time, we will reply directly to you all with email. Also, we'll be recording this webinar and posting it on both our the recording and the slides on our website and YouTube channel. Our presenter today is Al Wright, our PCB field application engineer. Al has been in the industry for over 35 years and has been with Epic for over 15. As the PCB field application engineer, he handles a wide range of responsibilities which range from reviewing PCB designs for manufacturability during the quote and design stage, interacting with off-site manufacturing facilities to solve technical issues during production. And Al has also worked on well over 50,000 different PCB designs from his start back in 1981. So without further ado, I'll pass it over to Al.
Okay, thanks, Keith. Yes, today we'll be going over how to choose and specify your PCB laminates according to the performance needs of your PCB designs. And the agenda will cover just a basic overview of how to call out FR4 materials, which a lot of you, I'm sure, already know, but it's always good to review. Then we'll get into some of the high-frequency materials that we offer and the properties of those materials, and then we'll go into some specific examples, applications, how the material is specified and described by the manufacturers, and how you can make good choices for what you need to use. So we're going to start with standard FR4, which is governed by the IPC spec number 4101C. The majority of boards can still be built using generic FR4 laminates without any significant negative impact on performance. We like to see you specify your laminate in accordance with the appropriate IPC slash sheet. The slash sheets are basically the different pages that describe the various materials, the properties, and the compositions. This gives us as the fabricator discretion to use a qualified product that we stock as standard, and therefore we can save you money and time. If your board doesn't have critical thermal or electrical requirements, we do recommend you call out your material per the spec. And there is a recent blog post by, I believe it was Chris Perry, on understanding an IPC 4101 slash sheet, and that is on our website, and that's the link right there. So if anybody's interested in seeing that, you can check that out. In addition to the full slash sheets, this is a page from 4101C. And there's full sheets that go in full descriptions, and then there's these little summary sheets. And you can see along the left here where I'm pointing with my mouse, the slash is 4101 is the spec, slash is the 124 spec, then you have the 126 spec, the 129 spec. And you can see there are differences in the types of epoxy, the different kinds of flame retardant in some cases, and the different glass transition temperatures. That's a very important reason to select the correct material, glass transition. So what if you need material performance that goes beyond the IPC minimums? Some FR4 designs have special requirements that are more stringent than the 4101C minimums, which are pretty wide. For example, even with a single IPC subtype, such as /126, the T sub G and the T sub D may vary widely, provided they meet those minimums, and the dielectric constant and dissipation factor can vary quite a bit too. So what do you do if your relatively complex PCB needs specific thermal or electrical performance characteristics that go beyond the generic properties called out in the spec? And the picture over here just shows this board needs a slightly higher TG, slightly higher TD, a specific dielectric constant, and it's calling out for impedance control. So all of those things are specific properties that you need to express to us so that we're selecting the right material, or so that you're selecting the right material. So what you want to do in those cases is to list those critical properties separately. You can still use the IPC 4101C callout, but add the special requirements to your notes so they won't be overlooked. And the fabricator will then select and suggest a laminate system which will meet all the requirements, including those which may exceed the minimum values from the IPC spec. And again, you look over here and I've highlighted the properties that are outside of the domain of 4101C's generic properties, and they're now in red. You don't need to put them in red, but you do need to express them to us so that we know what you need. Now there's a different classification of FR4 materials, high performance FR4s, and these, in addition to higher temperature, they have higher signal integrity as well. So when signal integrity is critical, there are specialty materials that offer excellent performance, but they still fall into the FR4 epoxy glass category. These are what I would consider transitional products, such as Melco 4000-13 EP and Isola iSpeed. And they offer outstanding thermal and mechanical performance, but they're also worth considering when they match the requirements of your design for signal integrity. And here's a spec sheet for the Isola iSpeed, and if I can find it, yeah, the dielectric constant for most FR4 products tends to be around 4.2 or 4. You can see it's a little bit lower here where my mouse is, and the loss on a lot of FR4 products ranges from about 0.20 down to about 0.14 or so. These are much lower. These are in the single digits. So you're getting a higher level of signal integrity with these type materials. And again, this is Melco 4000-13. Same story. These dielectric constants are in the mid to low 3s, and then the dissipation factors are around between 7 and 9. So again, that's good stuff for signal integrity. Now the very next step is high-speed, high-frequency materials, and these are basically dedicated for very high-speed performance. So for applications that exceed the limitations of FR4, it is necessary to consider stepping up to high-speed, high-frequency material types. And these materials typically have extremely low dielectric constant and dissipation factors, but the properties are defined in an entirely different specification from the FR4s, and this spec is called 4103A. And that's a picture of it over on the right. And when you're calling out your material per this spec, which most people don't do, most people actually select a specific product and design that into their board, but if you do use the spec, you'll find that it goes into more detail about the signal speed and the loss characteristics of the laminate, which are extremely critical in high-frequency designs such as antennas, radar, RFID products. If you don't specify a particular manufacturer's products, you can use Table 1.1-1 and 1-2 to specify the material in accordance with the specification. And on the next slide, I'll show you what that looks like. This is a similar code to what is used in 4101, where each one of these designations here correlates to something on the table. So 4103 being the spec, A being the revision number, et cetera, the copper weight. So all of these things in this first table are what you would find in the other spec, 4101. But in 4103, oh, I'm sorry, in 4103, there are some added properties that you don't see in the other spec: test frequency, dielectric loss, resin, filler, and reinforcement. So you can actually come up with a very long code of letters and numerals to designate your material in a very specific manner. Again, most people just pick the material from a particular supplier and they design that in, and that's how they specify it. But it's good to know that this exists. Now, which materials to choose? While there are specialty materials available for a wide variety of high-frequency applications, some are more readily available than others. And what we find are the commonly requested types of the Rogers 3000 and 4000 series, Taconic RF35 and RF45, every once in a while Arlon Q-clad or die-clad, but others are available. One thing to note, and this can be important in certain applications, your fabricator may not be UL certified for a particular product. It's an involved and costly process to get that certification for a particular material. So while a fabricator may be willing to build with a certain material, they might not be able to add their UL marking to the finished product. So you just have to keep that in mind if the finished product is going to be subject to UL. Make sure that you state that your product is a UL compliant product in your documentation too, so that we're aware of that, so that if we find out we don't have the certification for that material, we will tell you, and we will work out a solution one way or the other. Now, different subtypes of this high-frequency material have different compositions. Many high-frequency materials, such as PTFE, which is Teflon, can be difficult for fabricators to work with. Because of this, the material manufacturers have developed products which can be processed much more like FR4 types, and that helps the fabricators to stick more with their normal process sequences. Some of these materials, like the Rogers 4000, utilize hydrocarbon ceramic with glass reinforcement, and others, such as the Rogers 3000 series, combine Teflon with ceramic fillers, and we'll get into why that is in a minute. So the composition of the different subtypes, again, we have a little blurb on the left here from the Rogers 3000 series. These are ceramic-filled PTFE, and it goes into a little about what the applications are. And then on the right side is the Rogers 4000, which is non-PTFE, and it's for a different group of applications. And both of these are compatible with FR4, so you can actually combine them in Stackups with FR4, and they will process pretty normally with a couple of exceptions. So that's one of the reasons why a couple of slides back I said they were very popular laminate types. So the applications for the different subtypes, when you're selecting materials for the project, the manufacturer's product data sheets are a really good place to look for a wealth of detailed information. They have processing guides, they have data sheets, they have material safety data sheets, all kinds of stuff, and I can direct you to their websites if you're interested. In addition to explaining the material's composition and properties, the data sheet will also list applications for which the product is suited, which we saw a little bit of in the previous slide. Below are two more detailed examples from Rogers. On the left is, again, the ceramic-filled PTFE type, and on the right is the hydrocarbon ceramic glass type. So these are the same two materials we saw a couple of slides back, but this is the applications section of the data sheet. And you can see on the Rogers 3000, automotive radar, global positioning satellite, et cetera, on the right side, microstrip and cellular base station antennas, power amplifiers, RFID. So again, the data sheets are a great place to look to give you some direction, the type of material you're going to want to select. And here's kind of an application note, just showing one application you might have, the effective glass at microwave frequencies. In radar sensors that are used in accident avoidance and automatic braking sensors, the wavelengths are so short that just the effect of the signal passing over the glass reinforcement that's embedded in the material can cause small variations in dielectric constant and phase. And In most boards that wouldn't be all that important, but with those frequencies it is important, and with the volumes and the consequences of failure in automotive applications, you just can't accept failure. So you need to select a material that's appropriate for handling that kind of signal frequency. So here again we're getting back to the Rogers, an appropriate material with no glass. The Rogers 3003 uses no glass. Its physical properties allow it to function correctly in either an all Rogers or an FR4 hybrid multi-layer for automotive and 5G wireless. And again, here are some of the applications that came from that sheet 1 or 2 slides back. So that would be an appropriate material to select for that automotive sensing radar. Now, when you need to build a multi-layer with this high frequency material, here's an example of a simple 2-core lamination that uses just high-speed materials. There's no FR4 involved. What we're specifying here are 2 4350B cores, and they're laminated together with bond ply. Bond ply is basically pre-preg or glue that goes between the layers to stick them together. Notice that it's a 3-layer design, and the copper has been removed from one side of the second core prior to lamination. So if you see the orange here, those lines represent the copper surfaces. What would happen here is the copper would be removed from the top of the second core to create a copper, let's say 1 ounce over 0 ounces. Then it would be glued together to the other core, which has the other 2 circuit layers on it. You end up with a 3-core design. It's going to be slightly asymmetrical because you have 60 on this side, 60 on this side, but the 4320 bond ply adds 8 thousandths of thickness, so the distance between layer 3 and layer 2 is a little bit greater than between 1 and 2, but that's how that would be put together and laminated. Now, one thing I want to touch on before we go too much further, because it'll be relevant to the next couple of slides, high-frequency materials do cost significantly more than FR4. The multiplier tends to range from 4x to 8x, and that largely depends on volume. If you get a really big order that uses this material, there's usually some flexibility in the pricing, but the manufacturers, when they're dealing with small quantities, tend to take advantage of that fact to charge what the market will bear. So because of the cost, most fabricators don't keep a large supply of this type of material in inventory. And that lack of inventory means that the material is often bought as a spot buy as needed. And if the order is small, it may be subject to a minimum order quantity surcharge. So that's kind of how you get up to that 8x figure. You get a lot of charges thrown at you sometimes on those small orders. And in some cases, if you're in a hurry, you're also paying expedited shipping, which is just one more thing to think about. But if you can plan your project ahead of time a little bit, give yourself a little bit of extra time, some of that material cost, especially the shipping, can be at least made less obnoxious. There are also processing costs associated with these high-frequency laminates. Some of them have to do with additional scrap that can be generated if you don't know how to handle it properly, and some of them are just extra processing or extra equipment that you need to process certain steps the right way. So one problem that can cause scrap is incorrect surface prep before lamination. That can adversely affect adhesion. Sometimes that would be like scrubbing the surface so that you've actually polished it too smooth. It will no longer want to stick together when you laminate it. Again, you have to remember some of this material is actually Teflon. So you know, Teflon is known for not sticking. That's its most famous property. So you have to be very careful how you surface prep it. The other thing that can happen in surface prep is it can distort. Some of these materials are a little softer than what you're accustomed to with FR4, and they will stretch if you have say, some rollers that are too close together, they can deform the material. A lot of the fun with these materials is learning how to drill it, how to drill them. Ceramic types in particular shorten the drill life considerably, and the hole preparation may require different processing that not every fabricator possesses. And by hole prep, I'm talking about de-smearing the hole. All boards, after they're drilled, go through a cleaning process where the inside of the hole is cleaned out to remove any kind of residue that might have been dragged back through the hole when the drill was exiting the hole. And with these materials, you sometimes need to use different chemistries and different processes to get that out, and not everybody has them. So it's important that your fabricator understand the differences in processing before they commit to building some of this stuff, because anybody who's ever seen it done by trial and error, and I have, it's not pretty. Processing costs associated with high-frequency laminates, again, continued. We have here a table, and it just goes through, on the left column, these are the different classifications of material, and as you go to the right, it gives you the temperature, the coefficient of thermal expansion, that being how much the material stretches in various directions, and then just general dimensional stability, how reliable your multi-layer fabrication will be, how well your boards will laminate, and how good your electrical performance is. And so you can kind of look at that, and depending on what your application demands, what combination of properties your application demands, you can decide when these high-frequency materials might be appropriate or even necessary for your design, and which ones to use. Down below, this is getting into drilling conditions for the various PCB materials. And I won't go into a lot of the details here, but down at the bottom here, drill life is worth noting. And you can see for FR4 with a carbide drill, depending on the diameter of the drill and how many layers you're drilling through and so forth, you can get as many as 2,000 hits out of a single drill bit. Now you go over to this thermoset hydrocarbon, looking at as few as 75 hits. A more normal ratio would probably be the ceramic-filled PTFE, which is here. 250 hits would be about normal for that. So, you know, comparing the FR4 to the ceramic PTFE, you're talking about 2,000 hits versus maybe as few as 250. That's basically 8x. You know, there's that 8x number, same as the cost of the raw material. So again, there's a little bit of cost stacking that comes in with this type of material. But if you need to use it and it's the right material for the job, then you need to consider using it. One solution to taking some cost out of these boards, and this applies specifically to multi-layers, is to use what's called a hybrid construction. Because the material itself is such a large factor in the overall cost structure of the board, consider substituting FR4 materials at the non-critical layer positions. So if you have some positions that just aren't that important electrically, throw some FR4 in there. It's way cheaper. Certain high-speed materials are formulated for compatibility in such hybrid stack-ups. It's especially important to know that the coefficient of thermal expansion of the high-speed material needs to be closely matched to that of the FR4. Otherwise, the unlike materials will expand at different rates under thermal stress, and what happens then is your plated through hole interconnections can get pulled apart after a couple of thermal cycles, and that's obviously a bad situation. So you do want to select your materials wisely. And here is another one of those sets of tables. Down at the bottom is the thing I really wanted to illustrate. The typical coefficient of thermal expansion is given here, and it's in this column. You can see they range very widely depending on which material you select. The CTE can be very different. So you want to just keep an eye on that. You want to use materials that have a similar CTE to FR4. And again, the data sheets will point that out to you, whether a material is suitable for a hybrid construction or not. Now here's an example on the right of a more complex FR4 hybrid. This is a 12-layer. The high frequency material is not required at all positions, so if you look, the FR4 is being used at the non-critical layers to save cost. And if you think about a 12-layer board and you're using a total of 6 cores and you're able to substitute 4 of those cores with FR4, which is only, potentially 1/4 to 1/8 of the cost, this stack up on the right is saving you a ton of money rather than throwing high frequency material into all those positions for no particular electrical reason. So this is a good thing to keep in mind, that you can build hybrids, not necessarily with every combination, but with some combinations of materials. Again, it just says be careful to make sure that they're compatible. When you're planning your design, again, I keep saying the data sheets are great, but you want to design to available thicknesses and types because they're not infinitely variable. In particular, the bond ply is not infinitely variable in thicknesses. With FR4, you have several different types, but with the bond ply, it tends to be kind of a one-size-fits-all. So you need to be aware of that when you're designing your stack up and shooting for your overall thicknesses. You also need to know that sheet stock's generally sold in 12 by 18 or 18 by 24 sheets. So your board or your multiple boards needs to fit within an area that's at least about 1.5 inches smaller in both directions. So in this case, you're talking about for 12 by 18, you want a board or set of boards that fits within a 10.5 by 16.5 area. The reason for that is your fabricator needs margins around the actual boards in order to have to place tooling systems, plating clamp locations, sometimes coupons. It's kind of a sacrificial area that's required, but obviously you need to fit your board to the device it goes into as your first priority, but if you can shave a little off or make it a little bigger or whatever and fit it so that it fits those panel sizes, just be aware that they are what they are. And again, as I said before, consider FR4 and high-frequency hybrids whenever that's practical, because that will save you a ton of money in some situations. And here is the bottom part of one of the Rogers sheets, and you can see the standard thicknesses of that the 4003 comes in are listed here, and the 4350 are listed here. There's a slightly greater variety of 4350s. Panel sizes, these other sheet sizes aren't really practical, so stick with 1824 and 12 by 18. And down below, this is the point I was making about the bond ply. The bond ply really only comes in a couple of thicknesses, and it's not that customizable as it is with FR4, so you just want to be aware of that. So in summary, it's important to specify the material properties of the PCB type you're designing by referring to either the IPC spec or to manufacturer documents. Special high-frequency materials are definitely available to meet most critical performance needs, and they do get pretty exotic. I've tried to just stick with some of the more common ones here. You can often combine unlike material types within a single design to make your board more economical, and we can certainly help you at EPIC to select appropriate materials for your specific application. Towards that end, we encourage you to engage early in the design cycle, and that way you can get rolling, and you can ask questions along the way if you need to, and we will do our best to help you out. And with that, I am going to hand it back to Keith for a moment.
Thank you, Al. Well, I'll review some of the questions that came in, and just wanted to briefly mention some of the additional PCB-based products we offer here at EPIC. just in case not all of you are aware. We do custom battery packs, flex and rigid flex PCBs as well, our high reliability user interfaces and cable assemblies, energy efficient fans and motors, and again our core product, printed circuit boards. Next slide, please, Al. We also have facilities based around the globe that specialize in each one of our products, with also a dedicated product manager for each product line. So our battery pack and power management is done out of Denver, Colorado. Our user interfaces are down in Largo, Florida. Fans and motors are done here in New Bedford, Mass, and also in Wales in the UK. Our PCBs are done here in New Bedford, Mass, as well as in Shenzhen, China. Flex and rigid flex circuits we do out of Toronto, Canada, and our cable assemblies are also done at our Largo, Florida location. Next slide, please, Al.
Okay, so there are some questions, and I'm going to try to answer them. There's a couple that kind of have to be in a particular, suggest anyway that they be answered in a particular order to make the most sense. But I'll start off with probably the simplest one. Going back to FR4 materials for a moment, when you're calling out an FR4 type from the IPC spec, what are the common ones and what characteristics do they have? For FR4, these fall into two major categories, basically low temperature and high temperature. The low temperature stuff's perfectly suitable for the old tin lead, hot air solder level type assemblies. You know, the ones that actually have that on the bare board when you receive them. The higher temp is for lead-free and RoHS compliant type work because it sees higher soldering temperatures and oftentimes multiple thermal cycles, so it has to be more robust. So basically, if you need a low temp material, you want to call out the 4101/21 material. That has a glass transition temperature of only 115 degrees, but in reality, almost all of the products that are sold meet at least 130 degrees, and some go as high as 140. So it's pretty good stuff if you're doing a hotter solder level type board. If you're doing a higher temperature board, I always recommend that you go straight to the /126. That's 170 degree glass transition. It uses RoHS compliant bromine flame retardant and inorganic fillers. Real stable and really well suited for the high temperature applications. And so that's what I would recommend. /21 for low temp, /126 for high temp, and you shouldn't go wrong. Let's see, if you need to buy high frequency materials that are not in stock, how long does that usually take? Well, that's a really good question because that comes up all the time. So usually it can vary from a couple of days from up to 10 days, and it really depends on a lot of different factors. It depends on how exotic it is. If it's something they don't keep a lot warehoused, where they don't keep a lot warehoused, you know, you could be waiting for them to actually do a build, like they'll do periodic builds every 2 weeks or every however often. They wait till they have a demand built up for it. Other times, if it's like 4350 or 3003 or something, it's probably available from a distributor, and it could be a local distributor or somebody in the country anyway, and that's usually going to be a matter of just a few days. But it does, as always, it always pays if you're building something non-standard to, you know, try to get it on order as quickly as possible, and that can get us on the material ordering as quickly as possible. 3. Is it possible to V-score high-frequency materials? I've been told that's not a good idea. I would say that whoever said that was generally right. There are a few problems with this. One is that some of the materials are very soft, and kind of fibrous, and they don't really take well to being V-scored, because a V-score is basically two circular saws facing each other, and anything fibrous like that is going to get kind of torn up. It's also not going to snap very well, because some of these materials are very very pliable. They're almost like the lead sheet that you might use to flash a chimney on the roof of a house. They kind of have that feel. Some of them. Others are much more rigid. But in general, yeah, V-scoring that type of material isn't a great idea. The other thing is that there's usually copper all the way to the edges on these designs, and if you're V-scoring through copper, it's going to lift it all up. It's going to look like the edge of a can that you just ran through a can opener. It's going to be a lot of lifted copper. It's going to have sharp edges, and it could even pull away from the surface at some places, and peel a large strip away from the surface. And lastly, some of these boards are built very thin, and again, with V-scoring, with V-scoring being two circular saw blades pointed towards each other, there's a minimum distance you have to observe between those two blades before they're actually hitting each other, and so you need to consider that. And if you have a thin material, you can't even really make a meaningful cut into the board without violating that minimum distance. So yeah, I would say you typically don't want to V-score this, which is a shame, because V-scoring makes your material utilization, it improves your material utilization, but unfortunately it's not usually a great solution. Let's see. Okay, you showed us a couple of basic stack-ups. One was a very simple 3-layer, and the other was a hybrid with more layers but mixed with FR4. Are you able to do higher layer count multi-layers using just high-frequency materials? Yes, the answer to that is yes. I apologize, I did sort of skip to the FR4 hybrid because I was getting into emphasizing cost savings, but all high-frequency stack-ups are definitely possible when they're necessary. That whether it's necessary or not to build them all of high frequency is, of course, up to you and what your signal integrity needs are, but it is doable. And this one is, I guess, kind of related to that one. One of the data sheet pictures showed a material that it said could have different dielectric constants in the same board. How is that possible? And okay, I understand where this came from. This is because I put in just a small section of the data sheet, and it wasn't clear that that data sheet was actually applicable to a whole series of materials. I've been talking mostly about the Rogers 3003, but the Rogers 3000 series is actually comprised of 4 different materials: 3003, 3006, 3010, and 3035. And they all have very similar mechanical properties, so they can be combined into the same stack-up. But they all have different dielectric constants, which makes them really useful. If you have something where you have differences in your signal integrity requirements and your signal speeds and so forth, you can actually mix and match these in the same stack-up, and they'll behave the same way, they'll drill the same way, they'll process the same way, but electrically they will each be unique and different. Just to go through what those dielectric constant differences are, they're pretty wildly different in a couple of cases. The 3003 runs at 3.0, 3006 runs at 3.5, then the 3010 runs at 6.5, and the 3035 is 11.2. And that's kind of an unheard of dielectric constant, for people who are accustomed to dealing primarily with FR4. That's quite a number. So that's where the confusion came in on that. It's actually 4 different materials, and that's how it's possible to have different dielectric constants in the same stack-up for the same board. And the risk of running over, I think I'm going to cut the questions there at the first 5, and we will email you answers to other questions you may have over the next day or two. And I will say thank you for attending, and have a good day. Thank you.